Welcome to this tutorial on testing for goodness of fit and independence using a chi-square test of significance. You may be familiar with the Greek letter chi. It looks like this, an italicized X, but it is pronounced chi. And then we square it, so it is called chi-square. We will be using this chi-square as a test statistic for testing both goodness of fit and independence for categorical data. We will be using the chi-square goodness of fit test to determine whether a random variable follows a specific probability distribution. So for example, let's say we have 3 soft drink flavors: cola flavor, cherry cola, and just original cherry. We will define P subscript A as the probability of a customer buying the cola flavor, and P subscript B as the probability of a customer buying the cherry cola, and P subscript C as the probability of a customer buying the original cherry flavor. Now let's say that historical data shows that cola has 0.5 market share, meaning 50% of its customers buy the regular cola flavor. Cherry cola has a 0.3 market share, 30% of its customers buy the cherry cola flavor. And original cherry has 0.2 market share. Suppose the original cola flavor is changed and marketed as new and improved. After the new cola is introduced, a sample is taken to see if there has been a change in market share for each of the soft drink flavors. The following hypotheses would be used to test if this change has occurred. The null hypothesis would be the status quo. So H0 colon P subscript A is equal to 0.5, P subscript B is equal to 0.3, and P subscript C is equal to 0.2. If, however, the sample shows that the new and enhanced cola flavor has changed customer preferences, then we would find evidence to support the alternative hypothesis, and it would be stated as HA, the probabilities are not P of A 0.5, P of B 0.3, and P of C 0.2. In other words, those probabilities have changed as a result of the new and enhanced cola flavor. So let's say we take a sample of the past 300 purchases of our soft drink after the new flavor has been introduced, and we find the purchases as shown in this table of observed frequencies. The term observed frequencies means exactly what it sounds like. These are the frequency counts we observe from a sample of 300 customer purchases. After the new cola flavor is introduced, we find that 182 out of the 300 customers purchased cola flavor, 72 purchased cherry cola flavor, and 46 bought the original cherry flavor. Now we would like to test our hypotheses. Is the probability of buying one of these flavors still the same as in the null hypothesis? Or has the new and improved cola flavor changed the proportion of purchases for its flavor and also the other flavors, in which case we would find evidence to support the alternative hypothesis that the probabilities are not equal to 0.5 for cola, 0.3 for cherry cola, and 0.2 for original flavor. So what we see in this table is based on observed frequency counts from the sample. Now we have to construct what is called an expected frequency count table. In other words, if the proportions didn't change after the new flavor was introduced, then what would we have expected the frequency counts to be? Since the hypothesized proportion of cola purchases is 0.5 or 50%, then we would expect 0.5 times 300 or 150 of the purchases to be for cola. And we would expect 0.3 or 30% of the purchases to be for cherry cola. And we would expect the original cherry to be 0.2 of 300 or 60 purchases. Now we can construct a table similar to the observed frequency table, but this one is for the expected frequency counts that we have just calculated. And the table would look like this. Take a look at these two tables. The one on the left is for observed frequencies based on a sample of 300 purchases. The one on the right is for expected frequencies based on the hypothesized proportions of purchases for each flavor. What we want to know is if the new flavor has changed those proportions so that they are no longer what they were hypothesized to be. Let's take a look at the hypotheses again. The null is the status quo, and that is what we are calculating the expected frequency table from. The alternative is counter to that, and that is what we are looking for evidence of. So we take a sample of 300 and we find that 182 purchased cola. That's our observed frequency count. We would have expected 150 customers to buy cola if the true proportion is 0.5. But we found the observed frequency of 182. Now the question is 182 different enough from the expected 150 for us to support the alternative hypothesis that the true proportion is not 0.5? The same goes for the other flavors. We would expect 0.3 of 300 or 90 purchases of cherry cola, but we observe 72. Is that enough of a difference or enough evidence to conclude that the true proportion of cherry cola is not 0.3? And finally, for the original cherry, we expected 20% of the purchases, or 0.2 times 300, which is 60 of the purchases, to be for original cherry. But the sample shows only 46. So now we have to see if that is a large enough difference between what's observed and what's expected for us to no longer believe the null hypothesis. And that is where hypothesis testing plays a role. We have already stated our null and alternative hypotheses. Our next step in hypothesis testing, whether we use the critical value approach or the p-value approach, is to calculate a test statistic. The test statistic for this type of goodness of fit problem is called a CHISQ.TST statistic, and it looks like this. In the red box, you can see the formula we will be using. The italicized x is the Greek letter chi, so we have chi-square is equal to, and then we see here a summation sign. Capital sigma means to sum up everything after this symbol. On top of the symbol there is a k, and under the summation sign is I equal 1. That tells us what we are summing. Since k is the number of categories, at our soft drink example we have 3 categories, right? Cola, cherry cola, and original cherry. Then k is 3 for our example. So we are summing I going from 1 to 3. What we are summing is the following. Look at the numerator. We see O subscript I minus E subscript I, and then squared. So we are summing the squared differences of observed frequencies from expected frequencies. O subscript I are the observed frequencies, and E subscript I are the expected frequencies for each I category. And that is divided by E subscript I, which is the expected frequencies for each category I. Let's take a look at how we would compute the chi-square-test statistic for this example. To make the formula easier to compute, let's construct a table to break down the chi-square formula. To begin, we have the categories listed with their hypothesized probabilities. So we have cola, cherry cola, and original cola listed with their hypothesized probabilities of 0.5, 0.3, and 0.2 respectively. Now let's add a column for the observed frequencies. Remember, these were taken from a sample of 300 customer purchases, and this is what we observed from the sample. 182 purchased cola, 72 purchased cherry cola, and 46 purchased the original cherry flavor. Our next column will be for the expected frequencies. So if the hypothesized proportions of 0.5, 0.3, and 0.2 are true, then we would expect that from a sample of 300 customers, 150 would purchase cola, 90 would purchase cherry cola, and 60 would purchase the original cherry flavor. So now we have a replica of the tables from the previous slide, the observed frequencies and the expected frequencies. Our next column calculates the difference between the observed frequency column and the expected frequency column. So 182 minus 150 is 32, and 72 minus 90 is negative 18, and 46 minus 60 is negative 14. Our next column is the numerator of the chi-square-test statistic, so we take the difference in the previous column and square each one and get 1,024, 324, and 196. And finally, the last column puts all the pieces together, and we take each of the squared differences and divide by expected frequency. So we have 1,024 divided by 150, and we get 6.83. We take 324 divided by 90, and we get 3.6, and 196 divided by 60, and we get 3.27. Now, if you remember the chi-square formula, there's a big capital sigma or summation sign at the beginning of the formula. So we need to sum all these numbers to get chi-square. And we get a chi-square equal to 13.7. So we are done calculating our test statistic, 13.7. And now our next step is to look up the critical value. This time we look it up not in the z table, not in the t table, but in the chi-square table. To read a chi-square table, we will need alpha, so let's use alpha 0.05, and we will need degrees of freedom, and for a chi-square table, degrees of freedom is defined as k minus 1, where k is the number of categories. We have 3 categories in this example, cola, cherry cola, and original cherry, so our degrees of freedom would be 3 minus 1, which is 2. So we have alpha of 0.05 and degrees of freedom 2. Now we can look up the critical value in the chi-square table. This is a chi-square table. You can find one on the internet or in the back of your statistics textbook. We need to look under 0.05 for alpha, our level of significance. So down this column, and degrees of freedom was k minus 1, 3 minus 1, which is 2. So across and down, and we get a critical value of 5.99. So now we have the test statistic of 13.7, and we have a critical value of 5.99. Just like we did in the past using the critical value approach, we use the critical value as a cutoff point. So anything above the critical value, we will reject the null hypothesis, and below the critical value, we will say do not reject the null hypothesis. The chi-square distribution is always an upper tail positive distribution since chi-square is a squared value. The numbers will always be positive and upper tail. That's why we don't worry about splitting alpha in half. There is only one tail, the upper tail. Here is what the chi distribution looks like. The critical value splits the distribution into the non-rejection area to the left of the critical value and the rejection region in the upper tail area. So just like before, the tail area is the rejection region where our conclusion will be to reject the null hypothesis. Our critical value is 5.99 and it would fall around here. And our test statistic is 13.7 and it would fall someplace here in the rejection region, way above the 5.99 cutoff point. So now we are ready for the next step, which is to compare the test statistic with the critical value and come to a statistical conclusion. We can see the test statistic is in the rejection region, so using the critical value approach, we would reject the null and find that there is evidence that the proportion for the 3 soft drinks has changed from the original proportions. Now let's see how this would be done using the p-value approach. First, we need to look up the test statistic in the chi-square table. The test statistic was 13.7, so looking across the same degrees of freedom, 2 degrees of freedom, the test statistic would be around here, off the chart. Since the last number for 2 degrees of freedom is 9.21, then 13.7 would be to the right of that, and the p-value would be here, also off the chart, but definitely less than 0.01. The rejection rule for the p-value approach is to reject if the p-value is less than or equal to the alpha value, and do not reject the null if the p-value is greater than alpha. We saw on the chart that the p-value was less than 0.01, and 0.01 is less than the alpha value of 0.05, so the p-value is less than the alpha value, and we would reject the null and find evidence that the proportions have changed from the hypothesized proportions. They are not 0.5, 0.3, and 0.2 for the different soft drink flavors. This is the same conclusion we reached when we used the critical value approach. Now let's see how we would use Excel to calculate chi-square and a p-value. Here you can see a worksheet with the data and the formulas in the cells. First we have the categories and their hypothesized probabilities. The observed frequencies in the next column are given, and the total can be obtained by using the sum formula shown. Now, to get the expected frequencies in column D, we need to take each hypothesized proportion from column B and multiply it by the total in C5. Now that we have the observed frequencies and the expected frequencies, we are ready to calculate chi-square. Remember, the formula is observed minus expected squared and then divided by expected. And then each of those is added to get the final chi-square value. So first, let's get those summed differences squared and divided by the expected value for each of the three categories, and you can see the formulas for that in the red box. Earlier in this tutorial, I showed you how to calculate this by hand by breaking the formula down into more pieces, a column for observed minus expected, then a column for observed minus expected squared, and then finally this column of observed minus expected squared, and then divided by expected. Now we are ready to sum all of these up to get the chi-square value here. And finally, we can have Excel give us the p-value by using the function shown here with CHISQ.TST, CHISQ.TST, and then the range. And the range is C2 to C4, and if you look, you'll see C2 through C4 is the observed frequency range, comma, the expected frequency range. So we have in parentheses observed frequency range, comma, expected frequency range. The expected frequency range is D2 through D4. Once we have all these formulas in place, we can take a look at the output. And it would look like this. So you can see that the numbers here are the same as what we calculated by hand earlier in this tutorial. I'm sure you can appreciate how much easier and faster it is to use Excel, especially when there are so many categories to compute. The chi-square test statistic can also be used as a test of independence when we want to see if two categorical variables are independent. As we did before with goodness of fit, to test for independence, we will again compare observed frequencies with expected frequencies. To test for independence, the null is stated as H0, the null hypothesis, is that two categorical variables are independent, and HA, the alternative hypothesis, is that the two categorical variables are not independent. To better understand this, let's take a look at an example. Suppose we take a sample of 300 customers at a restaurant and ask them two questions, their choice of entree and their gender. As a result of their responses, we can construct this table of observed frequencies. This table is called a cross-tabulation or cross-classification table and organizes the data so that it can be viewed by both gender and entree choice. We can see by looking at the table that out of 300 customers, 170 were male and 130 were female. We can also see from their choice of entree that 155 out of the 300 customers preferred beef, 75 preferred poultry, 40 preferred fish, and 30 preferred a vegetarian entree. The table further breaks down the data into how many males ordered each type of entree versus how many females ordered each type of entree. What we would like to know is the preference for the specific type of entree independent of gender? If they are independent, then we should see the males and females ordering each choice of entree in the same proportions as they are represented in the sample. If, however, choice of entree and gender are not independent, then the two categories are associated in some way. Looking at the table, you might see that more females ordered vegetarian meals than males, even though there are less females in the sample. You can also see that many more males ordered beef, 115 of the males, than females. There were only 40 females who ordered beef. So just a casual look at this table tells us that we might be onto something, that there is an association or a relationship between gender and choice of entree. But you can't just eyeball a table and come to a statistical conclusion. We have to use a scientific methodology to come to that conclusion, and our methodology is hypothesis testing. The first step, of course, is to state the null and alternative hypotheses. So the null hypothesis would be that the two categories are independent. So we state our null that entree choice is independent of gender. Then our alternative hypothesis would be that entree choice is not independent of gender. What we are going to do next, as we did before, is to construct a table of expected frequency counts under the assumption of independence. This table is a table of observations from the sample. So these are our observed frequencies. We now need to get our expected frequencies. We will develop our expected frequencies based on the assumption in the null hypothesis that gender and entree choice are independent. To calculate the expected frequencies, we use this formula. E, our expected frequency for each observation, is equal to the row total times the column total over the grand total. The subscripts for the letter E are I and J, and that refers to the ith row and the jth column, since we will be looking across each row and down each column to get the expected frequency counts for each intersection or cell. Let's take a look at how this will be done for this table. Here again is the table of observed frequencies. You can see in the formula below that in order to construct a table of expected frequencies, we multiply each row total by each column total and divide by the grand total. So let's begin with a table that has row totals and column totals filled in. We get this information from the observed frequency table. The row totals are for the entree choices, 155 for beef, 75 for poultry, 40 for fish, and 30 for vegetarian. And we also see the column totals are filled in with 170 males and 130 females. And of course, the grand total is 300. Now we are ready to use the formula to fill in each of the empty cells with the expected frequency counts. Let's start with the first cell, which is males who ordered beef. So that is the first cell, row 1, column 1. And to calculate that, we take the row total, 155, times the column total, 170, divided by 300. Here's the row total, 155. Here's the column total, and here's the grand total. So 155 times 170 over 300, and that will give us the expected frequency count for that cell. Now for the next cell, we take the row total times the column total divided by the grand total. The row total is still 155 since this is still row 1, but now we have moved to column 2, so the column total is 130 and the grand total of course remains the same, 300. The next cell is row 2, column 1, the intersection of males who ordered poultry, and that is 75 times 170 divided by 300. Moving to the next cell, we get females who ordered poultry, and so that's row 2, column 2, and that would be 75 times 130 divided by 300. And we do the same for males who ordered fish, females who ordered fish, males who ordered vegetarian entrees, and females who ordered vegetarian entrees. And so now we have the entire table filled out. We just have to do the math on each cell, but I hope you get the idea of how to construct this table of expected frequency counts, row total times column total over grand total. Here is the table with all the numbers filled in. So now we have a table of observed frequency counts on the left and expected frequency counts on the right. As we did before, we want to calculate chi-square by calculating the difference between what is observed and what is expected under the hypothesis of independence. If gender and entree choice are independent, there should be no significant difference between what is observed and what is expected. If, however, there is an association between gender and entree choice, then we will see a significant difference between actual frequency counts and the expected frequency counts. To test for this significance, we use a chi-square test statistic. This test statistic looks very much the same as what we use for a goodness of fit test, but this one has two summation signs since we have to sum across each row and down each column. So the summation with I under it is for the rows, and the summation sign has I equal 1 to R on top of it. The R stands for the number of rows. So for our example, we have 4 rows, so the summation sign would have I equal 1 to 4, 1 being under the summation sign and 4 on top where the R is. The second summation symbol with the J under it is for the columns. And here we sum down each column. C refers to the number of columns. So J goes from 1 to C. For our example, we have 2 columns, one for males and one for females. So we sum across each row and down each column, and that's why there are 2 summation symbols. And what are we summing? We are summing the squared differences of O minus E divided by E, just as we did before. To make this calculation easier, let's put together a table and break down the formula piece by piece. Let's first make a column for all the entree choices and another column by gender. Then we can fill in the observed frequencies and the expected frequencies. All of these categories are from the previous slides across each row, beef, poultry, fish, vegetarian, and then each column, male and female. And all the numbers we have are from the previous slides as well. So now we are ready to calculate O minus E, that is observed minus expected. To get this column, we take each number in the observed frequency column and subtract the expected frequencies, and we get these numbers. Next, we square those values, and we get this column of numbers. And then we take the squared differences and divide by expected frequencies, and we get this column of numbers. But we aren't finished yet. We still have to calculate the test statistic chi-square, and to do that, remember, we sum across each row and down each column, so we need to add up all these numbers, and we get a chi-square value of 43.39. So now that we have calculated our test statistic, we can use either the critical value approach or the p-value approach to come to a statistical conclusion. Let's start with the critical value approach. We need to calculate a test statistic, which is what we just did, and we got 43.39. Now we have to look up a critical value. We will use a chi-square table, and we need 2 things, alpha and degrees of freedom. Let's use an alpha value of 0.01. And degrees of freedom for the test for independence is R minus 1 times C minus 1, where R is the number of rows and C is the number of columns. So degrees of freedom is 4 minus 1 times 2 minus 1, which is 3. Now we are ready to look up the critical value in the chi-square table under alpha 0.01 and 3 degrees of freedom. Looking on the chi-square table under alpha 0.01 and 3 degrees of freedom, we find a critical value of 11.34. So now we have the test statistic of 43.39 and a critical value of 11.34. Our next step is to compare the two and come to a statistical conclusion. Is the test statistic in the rejection or the non-rejection region? Take a look at the chi-square distribution. The rejection and non-rejection regions are split by the critical value, which is 11.34, and the test statistic, 43.39, would be somewhere out here in the tail area. So we would reject the null hypothesis and conclude that there is evidence for the alternative hypothesis that gender and choice of entree are not independent. In other words, there is a relationship or association between gender and choice of entree. We can also solve this problem using the p-value approach, and we will come to the same conclusion. In order to use the p-value approach, we must look up the test statistic in the chi-square table under the same degrees of freedom we used before. Degrees of freedom is R minus 1 times C minus 1, which is 4 minus 1 times 2 minus 1, which is 3. Looking on the chi-square table for the test statistic under 3 degrees of freedom, we find that when we look across 3 degrees of freedom, the test statistic of 43.39 would be around here. So the p-value would also have to be somewhere around here off the chart. And so we can extrapolate that the p-value would be less than 0.01. We don't know exactly what the p-value is, but it is certainly less than 0.01. And that's all we need to know, since the rejection rule is to reject the null hypothesis if the p-value is less than or equal to the alpha value, and do not reject the null if it is greater than alpha. We found our p-value to be less than 0.01, so it is less than alpha, and therefore we would reject the null hypothesis and find evidence that there is an association between gender and choice of entree. All of these calculations are made easier for us using Excel. On a spreadsheet, we would first need to import the data or type in the categories and their observed frequency counts. We see that in column A, we have the categories typed in, and in column B, we have the observed frequency counts. Next, we need to calculate the expected frequencies, and we see the formula in column G, where the row totals and the column totals are divided by the grand total for each cell for the males, and the same for the females. So we're letting Excel do all of these tedious calculations for us. Now we can let Excel tell us whether the differences between actual observed frequencies and expected frequencies are significant by calculating a p-value. To use the Excel formula for the p-value for chi-square, we type in CHISQ.TST, then open parentheses, and then the range of the observed frequencies, in this case that's B3 through C6, a comma, and then the range for the expected frequencies. Here it is G3 to H6. The output for these formulas would look like this. And we can see all the calculations that we did by hand are here, but most importantly, we have the p-value. You can see it is written in scientific notation because the number is so small, very, very close to 0. Remember, it was off the chart when we looked on the table. The letter E followed by negative 0.09 means that this number is in scientific notation, so to read the number you would need to move the decimal to the left 9 spaces and put zeros there. So this number is 0.000080 and then 202.867. Very close to 0 and certainly less than any alpha value that we would pick. So there's very strong evidence for the alternative hypothesis that gender and choice of entree are not independent events. That concludes this tutorial on goodness of fit using chi-square test of significance and the test for independence. I hope you enjoyed this tutorial and I hope you learned something.